Solve one problem on shape factor of the satellite which circles the Earth. We will read the given question. A small disc-shaped Earth satellite 1 meter in diameter circles the Earth radius 6250 km at a distance of 500 km from the surface. The flat surface of the disk is oriented tangential to the Earth's surface. The satellite surface has an emissivity of 0.2 and is at minus 25 degrees Celsius. Calculate the net rate at which energy is leaving the satellite. Assume that first, average Earth surface temperature is 27 degrees Celsius and is black. Second, satellite is in the shadow of the Earth. Third, the part of satellite surroundings not occupied by the Earth is black and at 0 degree Kelvin.
Let us understand the given data with the help of diagram. It is given that their satellite is of disc shaped and it is having orientation in the tangential direction to the Earth. Now for this disc shaped satellite we will consider there are two surfaces and which are in the circular cross section for the disc. Now emissivity epsilon for the satellite is given 0.2 and temperature of satellite minus 25 degrees Celsius. And then here this temperature of the Earth is given 27 degrees Celsius and it is mentioned that is it is black. Now if we observe the diagram, sun rays are coming from the bottom half portion of the Earth. That means this bottom half portion of the Earth is bright and the upper half portion is black. And this upper half portion, that is the black portion, is in contact with the satellite. Then the surrounding of the satellite is at 0 degree Kelvin and it is also black. Then the radius of the Earth is mentioned, we will say here as a capital R, and the distance of the satellite from the Earth's surface is also mentioned, we will say here as a small r. Now we will give here some numbers. So for the satellite I will mention here the number 1. Then for Earth I will mention here number 2, and for sun rays I will mention here the number 3. Now what is the question? Question is that we have to calculate rate of energy leaving the satellite. So by using the term shape factor, it is also known as surface factor or configuration factor or view factor, we have to find out the rate of energy leaving the satellite. So how we can define this rate of energy leaving the satellite? That is equal to rate of emission of energy, that is the rate of emission of radiant energy from the satellite minus rate of gain of energy. That is, we have to also find out what is the rate of gain of energy to the satellite. So we will give here the notation. So rate of energy leaving the satellite, Q is equal to rate of emission of energy, that is Q1, minus rate of gain of energy, that is Q2. So we have to first find out this Q1 and Q2, then we can easily find out this rate of energy leaving the satellite. So how to calculate rate of emission of energy? Now here emissivity is mentioned in the question for the satellite. So from that emissivity we will use the formula, that is we will use here the epsilon. Now we know that this satellite is of disc shaped and therefore it is having two surfaces of circular shape. So we will take here rate of emission of radiant energy from both sides of satellite is equal to 2 into epsilon into A1, because we have to take the two surfaces, that's why 2A1 that we will use into epsilon into sigma into T1 raised to 4. So sigma is the Stefan-Boltzmann constant and while the temperature T1, that is the temperature of satellite. So for any notations for satellite we will use here the suffix 1. Now we will put the value. So 2 into epsilon 0.2 area. So for this circular cross sectional area pi by 4 d square, and the diameter of satellite is given 1 meter. So pi by 4 1 square sigma 5.67 into 10 raised to minus 8 T1. So we have to take temperature in Kelvin. So here is the minus sign, so we will use 273 minus 25 raised to 4. So answer is 67.58. So this is the value of Q1. Now we will move for the Q2, rate of gain of energy. Now if we observe here, this total half portion, that is the upper half portion, is black. So how this energy is gained from the earth to the satellite? So it is also the radiant energy emitted by the earth, and it is moving from the surface of earth to the satellite. So here, for the rate of emission of the earth, how to calculate? That is the rate of gain of energy. That means rate of emission of the energy from the earth's surface, that we have to calculate. So we will use here some fraction of energy, that is the shape factor. We will use here the concept of shape factor, that is the fraction of energy radiated from the earth's surface and reaches to the satellite. So here this number is 2 and here is 1. So we have to write the shape factor 2 to 1, that we have to use. And then this fraction of energy radiated from this earth's surface reaches to the satellite, that is f of 2 to 1, and that shape factor, that is nothing but the rate of gain of energy. But we have to use the other parameters also, because the rate of energy emitted by this earth's surface will depend on the temperature of the earth also. Then it will depend on the Stephen-Boltzmann constant, and we have to also consider the area A2. That is, for this earth we have to consider the area. Now again, if we observe how we can write this formula, so rate of emission of radiant energy from the earth, that is equal to sigma, that is Stephen-Boltzmann constant, area A2, that is the area of the earth, f of 2 to 1, that is the fraction of radiation energy emitted from the earth and reaches to the satellite, that is f of 2 to 1, into T2 raised to 4, that is this temperature of the earth raised to 4. Now this is the formula, but we know that this whole emission of radiant energy is not getting absorbed by the satellite. Why? Because there is also the absorptivity of the satellite, that is alpha 1. So for this total emission of radiant energy from the earth, some amount is getting absorbed by the satellite when we multiply it with absorptivity alpha 1 to this whole equation. So energy absorbed by satellite is equal to alpha 1 multiplied by sigma A2 f of 2 to 1 T2 raised to 4. But we know that according to Kirchhoff's law, absorptivity of satellite is equal to emissivity of satellite. That means here I will say this is epsilon 1. Then according to Kirchhoff's law, we can say that this alpha 1 absorptivity of satellite is equal to emissivity of satellite. So I will write here alpha 1 is equal to epsilon 1. So instead of alpha 1, I will write here epsilon 1. So energy absorbed by the satellite, that is rate of gain of energy, Q2 is equal to epsilon 1 sigma A2 f of 2 to 1 T2 raised to 4. If we observe the equation for Q2, then we have to find out f of 2 to 1. That is, we have to calculate what is the fraction of radiant energy emitted from the surface of earth and reaches to the satellite. Now if we observe the size of earth and satellite, then this satellite is much smaller than as compared to the earth. So we can say that the radiant flux emitted by the earth is constant. That we have to consider, because f of 2 to 1, this earth is much big size than the satellite. That's why the radiant energy emitted by the earth is constant. So instead of f of 2 to 1, we will find out what is f of 1 to 2 by using or by applying reciprocity theorem. So if we apply the reciprocity theorem for this satellite and this earth, then a1 f of 1 to 2 is equal to a2 f of 2 to 1. So what is the value of f of 2 to 1? That is equal to a1 by a2 f of 1 to 2. Now we have to find out what value of f of 1 to 2, that is the radiant energy emitted by the satellite and reaches to the earth. So for that we have one formula. Now if we observe the radiant energy emitted by the satellite, we will consider here it subtends an angle of 2 alpha. That is, if I draw here one normal, that is one perpendicular line that will passing through the center of earth, then here will be angle alpha and here will be angle alpha. So this total angle will be 2 alpha. Now here is the formula to calculate the shape factor. So how to calculate the shape factor in between the satellite and earth? That is solid angle subtended by satellite, because the radiations are emitted from the satellite. So solid angle subtended by satellite divided by solid angle subtended by earth. Now we have one formula. So how to calculate solid angle subtended by satellite? So we will use here the total distance from the center of earth to the satellite is r plus r. So we will write here 1 divided by r plus r square. And solid angle subtended by earth. So here the total distance of the earth's surface from center is capital R. So it is 1 by r square. So when we simplify this, then this denominator term will move to the numerator, and this numerator, that is 1 upon r plus r square. So if we simplify this, then we will get r square divided by r plus r bracket square. So capital R is 6250 and small r is 500. So when we solve this, then we will get 0.85. Now we will put the value for f of 2 to 1. So f of 2 to 1, that is equal to a1 by a2 f of 1 to 2. Now this a2 and a2 is getting cancelled. So what is the equation? Q2 is equal to epsilon 1 sigma a1 f of 1 to 2 t2 raised to 4. Now we will put the value. So epsilon 1, that is 0.2, sigma 5.87 into 10 raised to minus 8. So this is the Stephen Boltzmann constant. Then A1, so area of the satellite pi by 4 into d square, that is 1 square. F of 1 to 2, that we have calculated 0.85, and T2, that is temperature of this earth, we have to consider in Kelvin, that is 273 plus 27 bracket raised to 4. So when we calculate this, we will get 61.85 watt. So what is the value of Q? That is the rate of energy leaving the satellite is equal to Q1 minus Q2. So Q1, that we have already calculated, and it is 67.5 watt. So value of Q is equal to 5.65 watt.